Hello, my name is Yeon, and today I'll be talking about TransINT, our paper accepted to AKBC this year. Since our paper is on knowledge graph embeddings, let me go over it briefly. What you see on the left is an example of a knowledge graph where entities such as John and Tom are represented as nodes, and their relations between them, such as is mother of, are represented as edges. One current trend of knowledge graph research is to embed these graphs to elements of R to the D. Another hot trend is to impose implication rules that are very natural to us, but may not be so natural to the embeddings of these knowledge graphs, such as is father of implies is parent of. So our question is, can we impose implication rules in knowledge graph embeddings in a way that's geometrically consistent? So let me more precisely define our problem statement. We first observe that relations are sets of ordered pairs of entities. So if you look at this diagram, you can see that the relation is father of in a knowledge graph can actually be a set that takes each head and tail, head comma tail as its element. So these are ordered pairs of entities, and we assume that we are given rules or hierarchy among relations. So we know that is father of is a set that belongs to is parent of. So our question is, can we define some space in R to the D that are isomorphically ordered as these sets of is parent of and is father of in R to the D? More precisely, we want to impose an if and only if relation between these sets and their equivalents in R to the D so that their orderings are isomorphically preserved. So we start from a popular method called TransINT. A popular view to interpret TransINT is that, well, in TransINT, if there is a head relation tail, then each of them are given a vector, and the relation is also given a hyperplane specific to it that entities are projected upon. So if there's Harry is parent of Tom in the knowledge graph, then in TransINT, they impose that Harry and Tom projected onto this hyperplane have to have difference equal to the vector for is parent of. So the traditional way to view TransINT is to do projection first and then difference. But we can flip the order of operation and then do the difference first and then projection. What we observe is that this new view produces a linear subspace that's unique to each relation, such that all the tail minus heads tied by that relation belongs to. So let's call this red line the relation space of is parent of. What we can further observe is that this T minus H is also an ordered pair of the head and tail entity as much as head comma tail is. So you can see the analogical analogy between the relation space and the relation set. So how can we make the relation spaces in R to the D be isomorphically placed as these relation sets that we have in knowledge graphs? So our methods is to impose two additional constraints to TransINT, and we can verify visually that if this green hyperplane is the relation space of is parent of, it contains the relation space of is father of, this blue line, and the relation space of is mother of. That means that all the T minus H's in is father of automatically belong to that of this green hyperplane, which is the relation space for is parent of. So with this approach, we prove that there's isomorphism between the relation spaces and the relation sets, and we achieved state-of-the-art performances in link prediction and triple classification. We also further discuss how to mine semantic relatedness and mine rules from relations with angles between the learned embeddings. Thank you.